we're going to briefly take a look at how to solve NMR and IR problems. We spent a lot of time on this a while ago, but it's been a while, so this is just a quick refresher. If we take a look at the tables for IR, you're going to need the ones that are in your reference packet. You can see that the first part is the hydrogen stretching region. And that's really where you're going to find your OH stretches, your CH stretches for alkenes, aromatics, aliphatics. Remember, those are things that are not aromatic. And mostly what you're looking for is there an OH or are there some CH stretches? Then we're going to take a look at the second section where we're looking at for double bond and aromatic rings. And that's going to tell us primarily, is there a ketone, aldehyde, carboxylic acid, or ester, looking for that C double bond O. We can also see an alkene stretch, C double bond C, or some substituted benzene rings. Everything below that, we're really not going to worry about. So we're not going to worry about the hydrogen bending region and certainly not worry about the fingerprint region. That ends up being too much for us to try to figure out. If you look at the key features of this IR, you can see that characteristic broad OH band around between 3,000 and 3,500. That's a pretty good indication that there's an alcohol. We will jump down and look to see if there's a C double bond O, and it turns out there's not. So it's not going to be a carboxylic acid, there's not going to be a ketone or an aldehyde, and it's not going to be an ester because we know we have an OH. So that's really the major information we're going to get from the IR. Most of the information beyond this we're going to get from the NMR. If we look at our NMR table, you can see that this gives us information about where the hydrogen is and what it's attached to, and where the peak will be on the x-axis of our graph. So if it's around 0.9, it's going to be a CH3. If it's going to be in the 0.5 to 5 range, it could be an alcohol. If it's going to be an aldehyde hydrogen, the one way at the end, it's going to be all the way at 9.7. If it's going to be the hydrogen on a carboxylic acid, it's going to be between 10 and 13. And one of the most important things to look for is the aromatic region. Between 6.5 and 8, if there's an aromatic or a benzene ring, we're going to see a peak in that range. The NMR is more complex than the IR, but we can get a lot of information from it. The first thing we can see is the position of the peaks along the x-axis. We can see that the one that's all the way to the left is probably going to be our hydrogen from our OH. We can get that from our chart. As we move towards the right, we see that there's a second peak, a third peak that is probably farther away from the OH, and a peak all the way around 0.9. Those are probably CH3s. The second piece of information we can get is we can take a look at how many hydrogens there are. So there's a 1 to 2 to 1 to 6 ratio. That gives us a total of 10 hydrogen atoms, although technically it could be 20 or 30 or 40. We're going to limit it to 10. So we know in our molecule it has to be in a 1 to 2 to 1 ratio. Sorry, 1 to 2 to 1 to 6 ratio. The third thing we can learn from our NMR is what the the hydrogen atoms are near. So the one all the way at the left is not split, it has no near neighbors, and that correlates with its being the hydrogen for an OH. The one all the way on the right is split in half. that correlates really well with two different CH3s on a carbon that also has a hydrogen. Just to the left of it, there's a peak that has a single hydrogen split into 7. That works really well in concert with the one to the right. So there's probably a carbon with a hydrogen and 2 CH3s and something else. And then the peak in around the 3.4 range, 3.3 to 3.4 range, is split in half, meaning it is probably next to the CH as well. And it's going to have a CH2. So all that information helps us figure out the structure. And now the last little piece is figuring out what the molecule is. So we will take a look at our possible problems, and we'll find one that has no benzenes. It does have an OH, and it has 2 CH3s that are identical with a carbon that has a hydrogen attached to it. So by putting all of it together, we figure out that it is 2-methyl-1-propanol. You're going to use the same process to figure out your unknown.